Hello students, welcome to ACE Engineering Academy. I am Ravi Sir, and in the today's session you will see some important questions of TSPSC AMVI exam. I will tell you here the important question and I will tell the solution, and with that solution there will be the revision of your chapter. Hence in the 1 hour session, in very small time, the 4th chapter I will revise, and that is benefited for you. Yes. Now see that which syllabus we have to see here. First see the syllabus. In your TSPSC AMVI syllabus, this is the chapter number 8, that is Engineering Materials and Production Technology. One session of this subject is already over and it is taken by my colleague Madhushekar Sir. And he completed the mechanical properties and testing of materials, iron-iron equilibrium diagram, iron-carbon equilibrium diagram, manufacture of iron and steel, heat treatment, ferrous, non-ferrous, metals and alloys. He completed that part. Now the remaining part is welding chapter, the machining chapter, in which the study of lathe machine is there, the drilling machine is there, milling is there, gear making, grinding is there, jig and fixture is one of the small topic. Then modern machining processes means non-traditional machining method, or also we are saying non-conventional machining method. That chapter question also we have to see in the today's session. And the next is foundry casting. Yes, up to that only. And the forging and mechanical working of metals also taken by Madhushekar Sir. Means in the first session that remaining topics are these forging, mechanical working of metals is already over. Now what are the topic I underlined here? That topic we have to see in the today's session. Yes. Now see that I am segregating it is chapter wise. Then you can see the first is casting, second is welding, third is non-traditional machining method, the fourth one is machining. Yes. That all are the topics. Yes. Now I want to start with the casting chapter. Now see the question of casting. In metal casting, solidification of molten metal completed at. Very important question. In metal casting, the solidification of molten metal completed at. The solidification of molten metal completed at. You can see the options here: pouring temperature, freezing temperature as a liquid, freezing temperature as a solid, and room temperature. Now this is very important concept is here, and I am going to explain that concept. Now see, this is the diagram. In this diagram you can see on the x-axis there is time, and on the y-axis the temperature is there. Yes, and this diagram is cooling curve for a pure metal. This diagram is for cooling curve for a pure metal. You can see the iron is a pure metal, we can apply this diagram to the iron. The aluminum is a pure metal, we can apply this diagram to the aluminum, right? But this diagram is not for alloys. The steel is the alloys, because in the steel there is a mixture of iron and carbon. Hence this diagram is not for alloys. This diagram is for only pure metals. Yes. Now see that in the diagram there is one temperature. Here I am showing that one temperature is known as Tp. Tp is the pouring temperature. Here is one temperature, that is a Tf. Tf is known as freezing temperature. And the last one is Tr. Tr is the room temperature. Yes. Now when we are pouring the molten metal at this point, then that molten metal means liquid metal is there. And this is the stage 1. You can see after the stage 1, here also we will get liquid only. But in the stage 2, liquid will convert into solid, and here we will get solid. And in the stage 3, solid will remain solid. While teaching, I am writing here some points. I am writing the points such as A, B, C, D. I am writing the points such as A, B, C, D. This is the point A. This is the point B. I am writing B point. Here I am writing the C point. And here I am writing the point D. Yes. Now just see that in the stage 1 what is happening. Just see this is the pouring temperature, means we are pouring the molten metal into the casting cavity, then that molten metal is in the liquid form. Then in the stage 1, you can see that there is a sensible heat loss. There is a sensible heat loss in the stage 1, and just see the freezing temperature. Here A to B, what is happening? The sensible heat loss is there, and temperature of molten metal is reduced from pouring temperature to freezing temperature. If I am taking the example of iron, what is the pouring temperature of iron? We are pouring the iron at 1700 degrees centigrade, and the freezing temperature of iron is 1539 degrees centigrade. This is the freezing temperature. Now you can see that the temperature reduced from pouring temperature to freezing temperature, but it remains in liquid form, hence it is a sensible heat loss. What is meant by sensible heat loss? Here you can see that phase remains constant. Phase remains constant, but the temperature is going to change from 1700 degrees centigrade to 1539 degrees centigrade. I am writing here these numbers for iron, but we can write for any pure metal. We can take for aluminum also, the pouring temperature is 800 degrees centigrade. We can write the melting point temperature means freezing temperature 660 degrees centigrade also we can write. Now what is the sensible heat loss? The phase remains same, but the temperature is going to change. Here there is some loss in temperature, and because of that the temperature is going to reduce. Some loss in heat, and that's why the temperature is going to reduce. Then this is the sensible heat loss. Next is, we can say that the latent heat loss. What is meant by latent heat loss? From in the stage 2, you can see that at the B point there is liquid, and at C point there is solid. This liquid is converted into solid in the stage 2. Which heat loss is there? Latent heat loss is there. Why latent heat loss is there? Because you can see it here. Phase is going to change. There are 3 phases of substance, that is the solid, that is liquid, and gases. Solid, liquid, gases are the 3 phases of substance. Here you can see that phase is going to change from liquid to solid, but the temperature remains same, that is freezing temperature remains same. For iron it is 1539 degrees centigrade, hence this heat loss is known as latent heat loss. Then you can see that at C point here we got the solid component. Then what is our question? What is our question? You can see what is our question. Our question is, in metal casting, the solidification of molten metal completed at pouring temperature? No. This is the pouring temperature? No. Wrong. Freezing temperature as a liquid? Just see that this is the freezing temperature as a liquid? No. This is also wrong. Next is freezing temperature as a solid. Now see here, this is the freezing temperature as a solid, and here you can see that it is converted into solid, hence the correct option is freezing temperature as a solid. In a metal casting, the solidification of molten metal completed at freezing temperature as a solid. But many students, what they are writing the answer? They are writing the room temperature, which is wrong answer. Then which is the room temperature? Here you can see that the room temperature is there. You can consider that room temperature as 25 degrees centigrade. Here the room temperature is there, and in the stage 3 it is happening, but the liquid is converted into solid at point C, means after stage 2. Why I have taken this question? Because this is the confusion for student. For many students, this is the common confusion for the student, and that's why I want to take this question. And again see one important concept here. The stage 1 and stage 2 is known as liquid shrinkage. Where the liquid shrinkage is going to happen? In stage 1 and stage 2, there is a liquid shrinkage. Why it is known as liquid shrinkage? Here just see, in the stage 1 the liquid remains liquid, but there is a shrinkage of molten metal. Means the volume of molten metal is going to reduce, and from B to C point, means in the stage 2 also the same case is going to happen. The liquid is converted into solid, then here is also the volume of molten metal is going to reduce, and finally we will get here solid component. This is known as liquid shrinkage. Here is also liquid, because before the stage 1 there is liquid, before the stage 2 there is liquid, hence it is known as liquid shrinkage. And where is solid shrinkage? Just see, this is the case of solid shrinkage. The stage 3 is known as solid shrinkage. Solid shrinkage. The stage 3 is known as solid shrinkage. This is the stage 3 is known as solid shrinkage. Here what is happening? At a C point there is a solid, and at D point also there is solid. But at C point the temperature is very high. Temperature of material, temperature of casting is very high, that is 1539 degrees centigrade, and at D point it is at room temperature. There may be the 25-26 degrees centigrade we can consider. Understood? These are very two important points in this chapter about the liquid shrinkage and solid shrinkage. And for your information, the solid shrinkage is also known as shrinkage allowance. Solid shrinkage is also known as shrinkage allowance. Yes, solid shrinkage is also known as shrinkage allowance, because whenever they are asking about the shrinkage allowance, the student has a confusion and they are telling that the shrinkage allowance means liquid shrinkage plus solid shrinkage, but it is 100% wrong. The solid shrinkage is also known as shrinkage allowance, right? Now, this question is completed, the first question is completed. In a metal casting, solidification of molten metal completed. Solidification of molten metal completed at C point. And what is the position of C point? The freezing temperature as a solid. And here we written the correct answer, freezing temperature as a solid. Yes, very important. Now see the next question. Shrinkage allowance is also known as, next best question. The shrinkage allowance is also known as, just here we discuss, the shrinkage allowance is also known as solid shrinkage. Now see, the shrinkage allowance is also known as liquid shrinkage, wrong. Solid shrinkage, correct. Solidification shrinkage, oh my God, what is that solidification shrinkage now? Yes, you got that the shrinkage allowance is the solid shrinkage, but the question is what is solidification shrinkage? Now you can see in that stage here, the stage 2 is the stage of solidification shrinkage. The stage 2 means from this point to this point, whatever the shrinkage is there, then it is known as solidification shrinkage. It is known as solidification shrinkage. And why it is known as solidification shrinkage? Because the liquid is converted into solid here. Just consider one example. Just consider at B point there are 1000 drop of liquid metal. 1000 drop of liquid metal. Then what is happening from B to C? How the liquid metal is converted into solid from B to C? This is the question. Just consider the 1000 drop of liquid drops at B point. Then at a B point, out of 1000 drop, the first drop of liquid will convert into solid. Correct? The first drop of liquid will convert into solid. And as the time is going here, just see, as the time is going here, the second, third, fourth, 10, 50, 100, 200, 500 drops will convert into solid at the middle, and 500 drop will be in liquid form. Then again, as we going here, as the waiting time is there, we are going to wait, then what happened? What happened finally at point C, the final drop, the last drop of molten metal, means 1000 number of drop of molten metal will convert into solid at point C. Then liquid is converted into solid, and that is known as solidification shrinkage. Then here what was the question? The shrinkage allowance is also known as solid shrinkage, but here I explained what is the solidification shrinkage. And again you can see here the option D, both A and B. Shrinkage allowance is also known as liquid plus solid. The many student, 90% student think that the shrinkage allowance is liquid plus solid shrinkage. That's why I kept this question here, right? And it is not important for your exam. This question is important for all exam in India, not for your exam only, right? Then any student want to revise this chapter, they can watch this video. If any student is preparing for any exam where the casting is in syllabus, then they can watch this video, correct? Yes. Now again, one important point I want to tell you here, in all the 3 stages, 1, 2, 3, in all the 3 stages, the shrinkage is going to happen. But whatever the shrinkage happening in 1 to 2, means reduction in volume, then riser is supplying required volume of molten metal. Means in stage and stage 2, just consider there is 100 millimeter cube of molten metal is available in the cavity, and in the stage 1 and stage 2, the shrinkage is going to happen and volume of molten metal is going to reduces from 100 to 99, 98, 97, 96, 95, then remaining molten metal is only 95 millimeter cube. Then loss of molten metal is 5 millimeter cube. Then who will supply that 5 millimeter cube of molten metal? The riser will supply. Who will supply? The riser will supply. Riser will supply that molten metal, and in the technical language we can say that the riser is compensating. What I am saying? The riser is compensating liquid shrinkage. Means whatever the liquid shrinkage is there, means whatever the shrinkage in stage and stage 2 is there, riser is there to take care of that. Means riser is supplying same volume of molten metal. But riser can't supply the molten metal in the stage 3. Why the riser can't supply the molten metal in the stage 3? Because after stage 2, means at point C, we are taking that casting along with the mold and we are putting that on vibratory machine. And we are giving the vibrational forces like that. Means stage 3 is happening on the vibratory machine. And there we are giving the vibration and mold is started breaking. Okay, now see next question. And you can also reply here. You can also reply here. I can see your messages. Yes, and after when you will watch this video, if you have any doubt, then you can message here. When I will see your message, I can reply you. I can clear your doubt. Yes, which of the following reduces the size of pattern? Now there is very famous one formula about the pattern size. Pattern size is equal to casting size plus or minus allowances. Plus or minus allowances. Hence we can say that the pattern size is equal to casting size plus we can write the machining allowance plus we can write the shrinkage allowance. Shrinkage allowance we can write minus we have to write the shake allowance. Minus we have to write the shake allowance. Why we are writing here minus shake allowance? Just see, in the classroom I am giving one example. I am saying that this pattern is of wood material. Just consider this pattern is of wood material and this is the cubical pattern. This is one of the cube we have to manufacture by casting method, and that cube has a side of 12 centimeter. Then all the dimensions of cube are same. Then all the dimensions are 12 centimeter. Now you can see that this 12 centimeter cube is the pattern. This is the wood pattern you can see. Then the pattern size is 12 centimeter. And here I can tell how I can say that the pattern size is 12 centimeter. The casting size is 10. I considered machining allowance 1, shrinkage allowance 1. Why I am taking that values? For understanding purpose only, right? Then the pattern size is 12. Now just see, we taken here the pattern size as a 12, but what is the problem with pattern size 12? In the shake allowance. Now see, when we have to remove that pattern, then this is the spike you can see, this is known as spike. And with the help of spike we are lifting that pattern. We are holding that spike and we are lifting that pattern. While lifting that pattern I am moving like that, and because of that some forces are going to occur on the mold wall. This is the mold wall. Some forces are going to occur on the mold wall, and because of that here you can see that the size of mold cavity is going to increase. Just consider the number. I said that I consider that the pattern size is 12 centimeter, but here just consider that because of shaking the size of casting cavity is increased and the size of casting cavity is now 13. Yes, it is now 13. Then when we are pouring the molten metal, then we will just the cavity size is 13 now, and when we are pouring molten metal into that, then here the 13 centimeter component is there, And if we are considering the shrinkage allowance, then it will be the 12 of size. If we are considering one machining, then we will get the casting size of casted component of 11 centimeter size. But what we want the 10 centimeter size. Correct? And that's why, what is the solution here? Don't take the pattern size as a 12. Reduce the pattern size. How we can reduce the pattern size? Here you can see the casting size is 10, machining allowance consider 1, shrinkage allowance consider 1, and consider shake allowance minus 1. And because of that, instead of 12, we can get the pattern size as 11. And when the pattern size is 11, then the casting cavity size will be 12. Yes? And after shrinkage, we will get 11 centimeter component, and after machining, we can get the 10 centimeter size of component, exact component. Yes. And this is the solution. Then, which of the following reduces the size of pattern? The answer is the shake allowance is reducing the size of pattern, and that shake allowance is also known as negative allowance. Here the pattern size is casting size plus or minus allowances. There are total 5 allowances are there. First is shrinkage allowance, second is machining allowance, the third is draft allowance, fourth is shake allowance, and fifth one is distortion allowance. Out of that 5 allowances, only we are writing the minus for shake allowances only. Hence that shake allowance is also known as negative allowance. Shake allowance is also known as negative allowance. Yes, now see the next question. Which of the following is the property of sand due to which it behaves like a fluid? Which of the following is the property of sand due to which it behaves like a fluid? Very important question. Yes, you can see the first porosity. What is meant by porosity, guys? Just see, here one casting cavity is there, pouring basin sprue is there, and in that casting cavity, we started pouring molten metal. We started pouring molten metal into that casting cavity. Then what happened when we are pouring the molten metal? Then whatever the air present in the casting cavity sprue, that air is started compressing. How that air is started compressing? Because initially the nothing is here. Nothing is here means air is there. Correct? Nothing is here means air is there. And when we started pouring molten metal, then whatever the air is present is get compressed. As the molten metal is entering, then the volume of air is started reducing, and because of that air get compressed. But when the pressure of air is greater than atmospheric pressure, then that air is started flowing outside through the porosity property of molding sand. Through the porosity property of molding sand. You can see through the porosity property of molding sand. Here it is going out, and that is known as porosity. Then which of the following is the property of sand due to which it behaves like a fluid? Then porosity is definitely, it is not a property. Next is fluidity. What is the case of fluidity? Fluidity means, fluidity is in the case of fluids. And which are the fluids? Do you know which are the fluids? The fluids are the liquids and gases. Liquids and gases are the fluids. Liquids and gases are the fluids. It is going to flow. But is the sand is going to flow like that, liquid and gases? No, not like that. But while making the mold, sand need to reach at each and every critical shaped component. And that is possible when we are adding the water into the molding sand, then only it is possible. If we are adding the water content in the molding sand, then that molding sand can reach to the complex shaped pattern. Is the complex shaped pattern, at the every corner it is going to reach, and that property is known as flowability. That property is known as flowability. The fluidity is the property of fluids and liquids, but flowability is the property of molding sand. Now next option you can see the plasticity. What is the plasticity? This is the question. What is the plasticity? Now to explain the plasticity, just come with one diagram. What is that plasticity? Yes, Now see what is the plasticity. Here you can see there is one of the pattern P I am writing, and here is total molding sand. This total is the molding sand, and that all are kept. Here one box is there. That box is known as mold box, or also it is known as flask. Also it is known as flask. One box is there. Now see, here is one box, and we are giving the ramming force here. That ramming force we can give by human hand, or also that ramming force we can give by machine. Now this is the total molding sand is present here, and we are giving the ramming force that, and because of ramming force, now we can see the level of that molding sand is up to this, but after some time the level of that molding sand will be at this point. Yes, will be at this point. Yes, it will compress. But after compression means first the level of molding sand is this. After a compression, the level of molding sand is this one. But when we are removing the force by human hand or machine, then again that level will not increase. It is known as plasticity. In the plastic, you know that the permanent change in shape is there. In the elasticity property, what is there? Just see, this is one of the metal. If we are giving the forces, then it will elongate, and when we are removing the force, it will regain its original shape and size. That is known as elasticity property. And in the plastic, the permanent deformation is there. Same case, here is also permanent deformation is there, and that is known as plasticity. Means firstly the level of molding sand was this one. Now this new level comes because of compression force. But when we are removing force, then again that level is not going to increase up to initial position, and this property is known as plasticity. Understood? Then plasticity is also not option. Now see the question number 5. This question number 5 is about the unfavorable temperature gradient. What is meant by unfavorable temperature gradient? Now you can see here the diagram of bottom gating system, because the in-gate is provided at the bottommost point. And here the question, the unfavorable temperature gradient can be seen in either it is in top gating system, bottom parting, or step gating system. Now what is happening? When the molten metal is entering here, that molten metal is entering with very high velocity, but as the level of molten metal is increasing, then slowly the velocity of that molten metal is going to increase, and very slowly the molten metal will go up to the top. And whatever the velocity of entering of molten metal, that velocity is going to reduce slowly, and when the molten metal will reach to the top, then here the flow of molten metal will stop, right? The flow of molten metal will stop. Now see that as the molten metal is going up, slowly going up, then heat transfer is continuous, and molten metal is going up to the top with very low velocity. Then what happened? The heat transfer is more, and because of more heat transfer, you can see the top region is cool and the bottom molten metal is hot. Means the molten metal which is going at the top, it is cool, and molten metal which is entering here, that molten metal is very hot. Hence you can see that this is not a favorable temperature gradient. What is meant by favorable temperature gradient? Favorable temperature gradient means if here is hot temperature, here is also hot temperature, then we can say that the favorable temperature gradient is here. But in the bottom gating system, the unfavorable temperature gradient is there, because the velocity of molten metal is going to reduce. That's why this casting cavity is filling very slowly, and the heat transfer is going on. It is filling very slowly. The molten metal is going to top very slowly, and heat transfer is continuous. That's why the molten metal which present at top side it is cool, and the molten metal which is at bottom side is hot, and it is known as not a favorable temperature, means it is an unfavorable temperature, and it is happening only in the case of bottom gating system. And the correct answer is option B, bottom gating system, right? Now see next. The sand used for making the cores is, which sand we can use for making the core? We have the option of green sand, loam sand, dry sand, none. Yes, the best option is dry sand. The dry sand we are using for making cores. Why the dry sand we are using? Why the dry sand we are using? Okay, just I saw one message, sir, please first explain production, sir. Actually, the one session is completed of Madhushekar sir, and that video is available on YouTube. Then you can watch their lecture. They just give the introduction of production, introduction of manufacturing subject there. Yes, good evening. Just I saw your messages. Yes, now we can continue. The dry sand we can use for making cores. Then why to use the core? I didn't come with the diagram here, but you can see that how to make the dry sand. We can take the silica sand plus clay, and instead of water here we are using the sodium silicate. Yes, and by adding that 3 we can get the dry sand. Why the name is dry? Because this mixture is very dry, just like a rice or wheat or jawari. We can take in hand and we can do like that, just like a sugar or groundnut. Such type of sand is here. Then how to use this sand to make the core? Then in that sand, in one core box, we have to put that dry sand, and in that core box we need to send one pipe, and through that pipe we have to supply the carbon dioxide. Yes, with the high pressure. Then when we are supplying the carbon dioxide, then that carbon dioxide will reach to each and every corner of that box, and that carbon dioxide will do the reaction with sodium silicate, and it will form some silica gel. Allow that silica gel to dry for 1 to 2 minutes, then it will give very good strength to the dry sand. Yes, and that sand we can use for making core. Then correct option is option C. The sand used for making cores, that sand is dry sand. Now see next. Cores are used to, why we are using the cores? We are using the cores for producing hollow casting. Yes, then what are the options? Form internal cavities in the casting. Yes, internal cavities means what? We can use the other word hollow casting. Hollow casting we can produce. Yes, hollow casting we can produce. Then cores are used to form internal cavities in the casting, means hollow casting it can produce. Just see the next option, improve mold surface, no. Form a part of a green sand mold, no. None, no. And the correct option is option A. Yes, here you can see this is the core. We can use the core, this is the core. And here you can see that we can make such a type of hollow casting, we can make here. And this is the core. The core, you can see here the core is rest in the core print. Then you can ask me, sir, what is the core print? This part is known as core print, and in that core print the core is fitted. Core print. This part is known as core print. This part is known as core print. Here is core print and here is also the core print. In that core print the core is going to sit, right? Now see next question, a casting defect which results in general enlargement of casting is known as. There is one casting defect which is not commonly explained anywhere, but there is one casting defect is there, and because of that there is enlargement of casting, and that defect is known as. What is that enlargement of casting that we have to see it now? Just see, we are pouring the molten metal into the pouring basin, then it is entering into the screw, runner and ingot. When the molten metal we are pouring, then because of metallostatic pressure, what is meant by metallostatic pressure? The metal, the molten metal is giving the force on that mold wall. These are the mold wall. This is boundary is the mold wall. And that molten metal is giving the force onto the mold wall, and because of that force, the boundaries of or the size of this casting cavity can increase. And if the size of casting cavity is increasing, then it is taking more volume of molten metal, and after solidification, we will get the bigger size of casting. We will get the bigger size of casting, right? And the defect, what is the defect is known as? That defect is known as swell. The defect is known as swell. You see the option C. The swell is the casting defect which results in general enlargement of casting. Right. Now see next. Question number 9. The riser must solidify. Just see, we are pouring the molten metal here. We are pouring the molten metal into the casting cavity. As we are pouring the molten metal into the casting cavity, you see that the molten metal is entering in the casting cavity, as well as that molten metal is entering into the riser. But the casting molten metal need to solidify first, means it will solidify first. And when this molten metal which is present in the casting cavity is converted into solid or is converting into solid, then the shrinkage is going to happen. And if the shrinkage is going to happen, then whatever the volume of molten metal is present in the riser, that riser need to supply that molten metal. Hence, the solidification time of riser must be greater than the solidification time of casting. Hence, what is the answer? You tell me. You tell me what is the answer. Riser must solidify before the casting solidifies. If the riser is converting into solid before the casting, then how riser can supply the molten metal? Option B, after the casting solidifies, and that is correct. And one student here gave the correct answer, option B. Yes? Yes. Now next and last question of casting. The investment casting is an example of semi-permanent mold casting. The investment casting is not a permanent mold casting like a die casting. Die casting is permanent mold, because die casting means metal mold we are using, and that metal mold is permanent. That metal mold is permanent mold. Then it is the permanent mold is the example of die casting. Expendable mold is the example of sand casting. Sand casting. And the permanent mold is the die casting. And semi-permanent mold is the investment casting. Why we are telling semi-permanent mold? We are not telling the permanent mold, or also we are not telling expendable mold. Why we are telling the semi-permanent mold? Semi-permanent mold we are telling because in one mold, here also in investment casting also we are breaking the mold and we are taking the casted component, and in the investment casting we can take the 5, 10, 15, 20 components in one mold only, but that number reaches up to 100 in the industry. 100 component also we can obtain in a single mold. Yes, but in the books we are telling that up to 20 value we are writing in the books, reference books. Yes, this was the last question of casting, and now, yes, we need to move for next chapter question, and that is the welding question. Now we need to increase our speed, right? Heat generated in the workpiece in case of resistance welding depend on. Heat generation is depend on. There is one simple formula, heat generation is equal to I square R into tau. Then the heat generation is depend on I square means welding current square, R means resistance of current conducting path, and tau is the time current is allowed to flow. Hence it depend that heat generation, Hg is what heat generation, it depend on all the three parameter I, R and tau. Then here the correct answer is all of above. Next, use of more acetylene with a less volume of oxygen. More acetylene, less volume of oxygen in an oxyacetylene torch produces which flame? Just see, the neutral flame means what? Oxygen to acetylene ratio is 1. and it is known as neutral flame. What is the oxidizing flame? Oxygen to acetylene is 1.15 to 1.50 is the ratio, means oxygen is equal to 1.15 to 1.50 of acetylene. Yes, then it is known as oxidizing flame. But here they are telling more acetylene with less volume of oxygen, then where we can obtain that ratio O2 to C2H2 is equal to 0.85 to 0.95. Here you can see that oxygen is equal to 0.85 to 0.95 of acetylene, means oxygen is less, acetylene is more. If the acetylene 1, then oxygen is 0.85 to 0.95. And this question is asking same, more acetylene they are asking, and it is happening in the carburizing case. This is the relation of carburizing case. Now see next question. The lap joint is preferred for plates having thickness. The lap joint. Now see, this is the lap joint and this is the diagram of resistance welding. Here you can see that the two sheets are there. This is the sheet number 1 and sheet number 2, and that sheet we are going to join by the resistance welding method. What is the thickness of sheet? Generally, we can take the thickness of, what is the difference between the plate and sheet? When the thickness is less than 6 millimeter, then we are saying it is as a sheet, and if the thickness is greater than 6 millimeter, then we can say it is as a plate. But somewhere you can also see the thickness is less than 5 millimeter, then only it is known as sheet. Hence don't worry about the sheet and plate. Yes, either 6 or 5, anyone you can consider. Now see here the lap joint, here is also lap joint, where the thickness of plate is lesser than 6 millimeter or 5 millimeter we are using. Hence here you can see the correct option is option C, less than 3 millimeter. Now see question number 4. Which of the following is multi-spot welding process? Multi-spot. The projection welding, the spot welding. Here the spot welding is not written, but here the seam welding is written. Resistance seam welding. What is meant by seam welding? The continuous weld bead is going to form between the two sheets. Just see, if we have to join that two sheets, this is the sheet 1 and this is the sheet 2, then what is the resistance seam welding? In that resistance seam welding, they are going to produce continuous weld bead. This is known as resistance seam welding. And here they are asking which of the following is multi-spot welding process, then definitely the seam welding is not multi-spot. Yes. Then next is projection welding. Yes, in the projection welding, we can produce the multi-spot at a time, hence the projection welding is the correct answer. We can produce the multi-spot at the same time, 2, 3, 4 spot we can produce with the help of projection welding. Hence which of the following is multi-spot welding process, that is the projection welding. Yes, now see the diagram, this is the diagram of projection welding. You can see this is the electrode here, you can see this is the electrode. And this is also one of the electrode, and this is the plate 1 and this is the plate 2. The plate 1 and plate 2 we want to join at this spot and this spot. Then at the same time we can join we can make the two spot at the same time, and this is the diagram of projection welding. Here the correct answer is projection welding. Now see next, is the group of fusion welding process that uses a combination of heat and pressure. Just see the example of resistance welding. Here the electrode is giving the pressure. Yes, and also we are giving the current. And because of current, the heat is going to generate here. And because of heat, one nugget is going to form. One nugget is going to form. One nugget is going to form. This is one of the nugget. Nugget is going to form here. Then you can see that with the application of pressure and heat, the joint is going to produce here. Then is the group of fusion welding process that uses the combination of heat and pressure, and it is known as resistance welding. In the resistance welding, we are using the combination of heat and pressure. If we have to speak about the gas welding, then only heat. Arc welding, only heat. Yes, and in the solid state welding, we are using the pressure also, or there are number of different 566 are the solid state welding process. In some welding we are using only pressure, some only we are using heat, but here in resistance welding we are using the combination of heat and pressure both. But in the solid state welding, direct we are not providing heat to the joint, but by rubbing action we can produce the heat like that. Just see, this is one sheet, this is the other sheet, do the rubbing action here, heat is going to generate, and then give the high force, then only the joint can produce. But no need to supply the heat. But in the resistance welding, heat and pressure both need to supply. Its answer is resistance welding. Next, time period during which forge pressure is applied to the metal piece. Forge pressure is applied to the metal piece. Yes, I got here many answers, and please you try to give the answer here, then it will be more interesting. Time period during which the forge pressure is applied to the metal piece, and that time period is known as forge time. That time period is known as forge time. Also we are saying as squeeze time. Also we are saying squeeze time. Squeeze time. Also we are saying the squeeze time. Yes, here I am using the word forge time. Both are same. In gas welding, the cylinders are filled with oxygen at about. In the gas welding, the two cylinders are there. One cylinder is oxygen cylinder, second is acetylene. In the oxygen cylinder, the oxygen is filled with some pressure, and that pressure is around 140 kilogram per centimeter square. So some people can say, sir, it is 130, some can say it is 150, no need, no any problem. It may be 120, 130, 40, 50, 60 maybe, that around values are possible. No one is putting exact 140. This oxygen is stored at 140 kilogram per centimeter square pressure, and the acetylene is stored at a pressure around 20 kilogram per centimeter square. If they asked here, in a gas welding the cylinders are filled with acetylene, then I need to write the answer option A, that is 20 kilogram per centimeter square. But here they asked about the oxygen, his correct answer is 140 kilogram per centimeter square. Next, arc blow can be reduced with, arc blow can be reduced with, just see the diagram. This diagram with the direct current straight polarity, this diagram with the direct current not a straight polarity I come with, this diagram with the direct current reverse polarity. What is known as direct current straight polarity? When the workpiece is connected to positive terminal, electrode is connected to negative terminal, then it is known as direct current straight polarity. Here the workpiece is connected to negative, electrode is connected to positive, hence we are saying it is direct current reverse polarity. What is direct current straight polarity? Workpiece is connected to positive and electrode is connected to negative, then it is direct current straight polarity, DCSP. And now this is DCRP, direct current reverse polarity. Then you can see that the arc blow can be reduced with, arc blow can't reduce with direct current straight polarity, arc blow can't reduce with direct current reverse polarity, arc blow can reduce with only alternating current high frequency. Now see the diagram of alternating current high frequency. What is the case here in alternating current high frequency? Firstly, the workpiece is connected to positive terminal, electrode is connected to negative terminal. Suddenly the polarities are changed and workpiece is connected to negative, electrode is connected to positive, and it is happening continuously. Yes, and this topic requires to explain 30 minutes. Here I am not explaining, and because of that polarities are going to change, and therefore we can avoid the arc blow. But I will tell you what is that arc blow. Arc blow means arc is flowing. Arc blow means arc is moving. Arc is flowing. How the arc can flow? Just see, this is the electrode. Then arc can go here like that, or arc can go here like that. It is known as arc blowing, arc flowing, and which can avoid with alternating current high frequency. Which of the following resistance welding is non-fusion welding process? Guys, resistance welding is the fusion welding process. By melting the base metal, we can produce the joint. By melting the edges of parent material, we can produce the joint, is known as fusion welding. But resistance welding is a fusion welding. But out of resistance welding there is one method which is non-fusion welding method, and for the most of the videos I am taking this question because it is very important. The spot welding is the fusion welding, resistance welding is the fusion welding, the projection welding is also fusion welding, but the percussion welding is the non-fusion welding, and the correct answer is percussion welding. Just see the example of percussion welding. In the percussion welding, you can see that these two rods are there, or also we can say that the two shafts are there. There are the two shafts are there, or two pipes are there, also we can say that. But now in this diagram you can see the two shafts are there, and just here these two faces here, and when the power supply is given then the heat will generate here. When the heat will generate, then this part of both 1 and 2, this part of both 1 and 2 shaft will be the softer part, then give the force percussively, means suddenly from both sides, then some metal, soft metal will come like that, come out, then we can remove this metal by machining. Here the metal is not converting into liquid. If the metal is converting into liquid, then it can fall down. It can fall down from the here, hence it is not converting into liquid. Yes, it will be the soft material, but it will not convert into liquid. And if it is not converting into liquid, hence we are saying it is a non-fusion welding method. It is a non-fusion welding method. Yes, very good answer. Pradhu, your answer is right. Yes. Now see next question here, and last question of this welding. Fusion welds made without the use of filler metal. Welding can be done without use of filler metal, without use of filler rod, then that welding is automatic. And automatic means it is the autogeneous welding. You can see this is the autogeneous welding. Its correct answer is what? Autogeneous welding. Then fusion weld made without use of filler metal is known as autogeneous welding. Automatic welding is possible, no need to use the filler rod. Understood? Yes. Yeah, now see with the first question of NTMM, that is a non-traditional machining method. Which of the following is thermal energy process? The thermal energy process means in which process the heat is going to generate, in which process the melting of material is going to happen. It is not happening the melting of material in electrochemical grinding or electrochemical machining. It is not happening in water jet, it is not happening in ultrasonic, but in the laser beam machining, the metal will convert into vapor. First the metal will convert into the molten metal, then suddenly into vapor, and this is known as thermal energy process. Then laser beam machining is the thermal energy process. Also I can say that electron beam machining is also thermal process. Then very famous method, electric discharge machining, is also thermal energy process. Next question. High frequency mechanical energy is transmitted to horn and tool assembly with a known amplitude of around, what is that amplitude here? Yes, do you have any option here? Just tell me this answer, because the amplitude, that value, yes, in the class I am giving that value, but for student it is very difficult to remember that value. Then tell me the correct answer, I am waiting for your answer. And the very first method I am teaching, and that method is ultrasonic machining I am teaching, and you need to give the answer. Yes, now see that, yes, one student gave that answer, but just see. What is meant by amplitude? First you have to see. The amplitude means, just see, in the ultrasonic machining method, the tool is at this position and this tool is vibrating from this position to this position. The tool is vibrating, means always the tool is covering that distance like that. It is going up to bottom, again top, this distance, and it is known as amplitude. And that amplitude in ultrasonic machining method is around 10 micrometer. to 100 micrometer. Yes. What is the option here? Yes, 50 micrometer is the option and it is correct option. Next, the energy required to create a spark is called as spark energy. The spark energy depends on, there is one formula for spark energy, 1 by 2 C Vd square is the formula. Then what is the Vd? Vd is the discharge voltage. Vd is the discharge voltage and correct option is option D, discharge voltage. Not charging time, not a discharge time, not a supply voltage, the correct answer is discharge voltage because the spark energy or energy formula is equal to 1 by 2 C Vd square and what is the C? C is the capacitor. Perfect vacuum is maintained. The most of the time I am repeating that question because this question is very important and the perfect vacuum is required only for one machining method, that is electron beam machining. The perfect vacuum is not required for laser beam machining. The students are facing confusion. Some students are telling, sir, laser beam machining also. No, only the vacuum is required in electron beam machining. Yes. Not in electric discharge, not in ultrasonic. Next question. Which of the following statement is not correct for unconventional machining process? Not correct. Not correct. You need to focus that word. You need to read the question carefully. Not correct means you will see the meaning or correct sentences. The first sentence is this statement is correct. Tool material need to be harder than workpiece material? No. Tool material need to be harder than workpiece material? No, it is not required in non-traditional machining method. But if we are working on the lathe machine, then it is required. If you are working on the CNC machine, then it is required. But in non-traditional machining, it is not required. Hence, this first statement is not correct. And in that question, they asked which of the following statement is not correct for the unconventional machining process. The first statement is not correct. Next, very soft material can be machined. Correct. In the non-traditional machining method, very soft material can be machined. Tool is never contact with job. Correct. Highly brittle material can be machined like glass. Correct. Next, now see some few questions on the chapter machining. You can see the few questions on the machining chapter. You can see. Yes. Which of the following is natural abrasive? Just in the grinding machine, we are using these 4 types of abrasives: aluminum oxide, boron carbide, diamond, silicon carbide. And out of that, the option D, that is the silicon carbide, is the natural abrasive. Silicon carbide is the natural abrasive. And remaining 3, aluminum oxide, boron carbide, diamond, are not natural. They are the synthetic, means they are the man-made. Yes, these are not natural. Very easy. This is the question of grinding machine. The correct answer is option D. Which of the following statement is true about the down milling? There are 2 famous milling are there. One is up milling, second is down milling. What is the advantage in down milling? The direction of milling cutter and direction of workpiece remains same. Hence the forces and power required is less and forces required is less. Hence the wear of tool is less, then tool life will be better. Now see which of the following statement is true about down milling. The option is correct. Tool life is longer. Power consumption is more. No. Power consumption is low. Tool wear is high. No. Tool wear is low. Tool life is shorter. No. Tool wear is high. No. Tool wear is low. That's why the tool life is longer. Power consumption is low. That's why the tool life is higher, longer. Forces coming are low or less forces are coming. Hence also the tool life is longer. Next, single point cutting tool used. Now it is a tough question because drilling, milling, shaping, grinding, all people say that all are multi-point cutting tool. Multi-point cutting tools are there. Wrong. The drilling is multi-point cutting tool. Milling is multi-point cutting tool. But guys, in drilling, a number of single point cutting tools are there, and when we are combining that all single point cutting tool, then we get the multi-point cutting tool in the drilling. Next, milling is the multi-point cutting tool. Drilling, this is the grinding. In the grinding, the number of single point cutting tool we are taking. number of single point, and it is a multi-point cutting tool. Drill is also multi-point cutting tool, milling is also multi-point cutting tool. And what about the shaping? The shaping is only the single point cutting tool. In the shaping, we are producing one slot. Just see, this is the workpiece, and in that workpiece we want to produce the slot, then we are producing the slot. The slot we produced here by using the shaping tool, and that is the single point cutting tool only. Yes, point angle used for hard material. Guys, you can see that the point angle used for hard material is greater than 118 degree. The point angle in the drill, for the drill tool we are using the point angle, and for hard material we are using the point angle greater than 118 degree. That point angle we are using. Then less than 118 degree, no, it is wrong. 45 to 50 degree, yes, but 45 to 50 degree here is wrong, but 45 degree to 50 degree we can use for soft material. We can use this angle for soft material. We can use this angle for soft material. And here the 118 answer also we can see the correct. If this option B is not available here, greater than 118 degree, then standard point angle is 118 degree. We can select the option, but more correct option here the B, where for hard material we are using the angle greater than 118 degree. Now see the last question here. Out of all conventional machining methods, highest specific cutting energy is required. In which method the highest specific cutting energy required? This is a big question. Either it is turning, milling, reaming, grinding. Correct option is option D. The grinding requires highest specific cutting energy. Why it's so? In the grinding machine or in the grinding tool, I need to say grinding tool, whatever the abrasives are there, the number of single point abrasives are there. But while machining, only 1/3 of abrasive will work as a cutting tool, and remaining 2/3 is simply rubbing onto the workpiece. Only 1/3 is cutting the material, the 2/3 is only rubbing at the workpiece. Understood? And because of that, wastage of energy is there. 2/3 is simply rubbing, not cutting any material, and therefore only one method is there, grinding, which required very high specific cutting energy. Yes, now I tried here to give the good questions, to give the better revision in only 60 minutes of lecture. Yes, and I want to say you thank you for attending this session, and I hope so you completed your all the study. Your revision is also here at the ACE online platform on the YouTube. This video is available on the YouTube, and you did the revision also, or your revision is going on. And finally, I want to say you the thank you as well as all the best for your exam.